Howdy folks, in this section we are going to study lines and planes. Let's start off with lines. So you've studied lines extensively in algebra and calculus, but what we'd like to do is we'd like to start describing lines not in terms of the equations that we're familiar with, but in terms of vectors, the objects we've been studying recently. So I'd like to come up with some vector equations that will describe lines. Why would we want to do this? Well, the biggest reason is that once we give a vector description of a line, it actually very nicely extends to higher dimensions, minimizing the amount of work we need to do. The same will be true for planes, which we will define in R3, and then hyperplanes, which are the same version of a plane in higher dimensions. So just as a reminder, in algebra, we might have a line passing through space like this. And sometimes folks like to think about it in terms of a line passing through 2 points. That's a perfectly good way to talk about a line. But another way to look at a line is to say, okay, the line is going to pass through some initial point, which we could label x naught, comma y naught, and that line has to have a direction. And as long as that's a non-vertical line, then we've got the direction called the slope that tells us where we move, where we could travel to the next point based on some ratio that you've called rise over run. So that's the way we just talked about lines in algebra. So here I've got the point slope form of a line. Y minus y naught is equal to m times x minus x naught. And another way of thinking about this is in 2 space, once I assign a point, x naught, y naught, and once I assign a direction, I've uniquely determined that line. There's no other line that will pass through that point with that particular slope. So a line is uniquely determined given a point and a slope. Now in your Calculus 2 class or in some other class as a prerequisite for this, you've learned what are called parameterizations. And a parameterization is another way of trying to describe graphs. And what we do is we define some new parameter. Usually we pick, if there's just one parameter, we pick the variable t, although you could pick any letter you want to represent that new parameter. And so what we might do, and hopefully you saw this before, is we'll introduce like a notion of time to this scenario where maybe this is where t equals 0 and maybe this is where t is equal to 1 and here's where t is equal to 2, here's where t is equal to 3, and we have a sense of, it's almost like there's motion to this graph where the way most of us like to interpret, we say, okay, at time t equals 0, that's why we use t to think of as time, the dot is here, and then as time elapses the dot moves along this line, and the collection of all of the dots that the parameterization gives us, that whole collection together, that graph is called the graph of this line or whatever it is we're tracing out. So what I'd like to do is I'd like to give a parameterization for a line. So solving the point slope form of the line for y, we get y is equal to m times the quantity x minus x naught plus y naught. Now what we do in a parameterization is we're going to let x equal some function of t. And when you do parameterization, a lot of times students have a hard time with this. You can pick any function for any function of t here for our independent variable x. So we can pick anything. We can pick any function. Often, when you don't have a particular preference, we will let x equal t, and that's how we start the parameterization. But we could pick any function of t that we want here, as long as it's able to take on appropriate domain values that help us run through the graph that we're trying to trace out. So there, I guess, not any function, but there's infinitely many possibilities for the function we could pick. But in my case, and so why I'm not reviewing parameterization, because I'm not going to pick what's called the standard parameterization here, I'm going to pick, let's let x equal t plus x naught. Okay. Folks, if you don't feel comfortable with parameterization, don't worry. You will be comfortable with it by the end of this course. We're going to do a whole lot of it. So I don't think it's clear why I chose for my parameterization x is t plus x naught, but hopefully by the end of this exercise you'll see why I chose that. All right, once I pick x to be some function of t, notice that my dependent variable, in this case y, is determined by the choices that I've already made. So in this case, y is going to be m times t plus x naught minus x naught plus y naught. So x was an independent variable, in fact the only independent variable. I had a choice of what function of t I wanted to put there, but once I did that, then I had to replace the x in my function for y in terms of that parameterized variable. Okay, cleaning that up slightly, that would give me y is mt plus y naught. Okay. So I've got these two equations here. X is equal to t plus x naught, and y is equal to mt plus y naught. And I'm going to do something interesting. Maybe you've done this before, but what I'd like to do, and zoom in there a little bit, what I'd like to do is I'd like to represent this as a vector. So there's xy is equal to, and I'll reorder it slightly, x naught plus t and y naught plus mt. Now you might say, what allows you to do that? Well, the information contained in this system of equations right here is the same as the information that's contained in this vector statement right here. Remember, what does it mean for two vectors to be equal? Well, if I have coordinates for them, they have to have the same coordinates. So that means that x must be equal to x naught plus t, and y must be equal to y naught plus mt, so this information's the same. Then, what I'd like to do, and I'm sorry to run out of room on you folks, I'm going to rewrite this as xy is equal to, and I'm going to rewrite this in terms of the addition of a couple of different vectors. So I'm going to rewrite this expression on the right as the vector x naught y naught plus t times the vector 1m. Okay. Now you might be saying, why did I do this? Okay. And that's a good question to ask. But before we answer that, let me just point out that I can recover all of the information that I had from the parameterization up here. And so I can recover the line just from the vector equation that I've given. So we get that x is equal to x naught plus t, and y is equal to y naught plus tm, which is exactly what we had in that system of equations. Okay. This is going to motivate how we're going to think about lines, not just in R2, but in higher dimensions. And the key that I want to point out here is that my position could be thought of as some initial position plus some parameter t times a direction. That direction is related to the slope. So what we've done here is we've somehow encoded the slope as a direction vector into this problem. Okay? And we start off with some initial position that we want to talk about. All right, parameterization is something that we'll continue to explore, but what I'd like to do now is let's return to the idea of trying to build the equation of a line using vectors. So one way to think about this is that what I could take is a collection of vectors, and we're going to do this in R3, but we could do this in any space, a collection of vectors, and in this case I'm arranging them so that if I were to connect all of the tips of these vectors together, what I end up with, well, up to my ability to draw these vectors, what I end up with is a line in R3. Okay. So what I want you to do, and we're not going to draw this picture very often because it gets so cluttered, but I want you to think of any, in fact, it could be any curve, in this case it's a line, but any curve as a collection of tips of vectors. And what I'd like to do, just to get us started, is the first vector I drew was about this vector right here, and let's call that point that we land at P naught. So P naught is some point in whatever space we're working with. But we've learned that if P naught is a point, we can give an equivalent position vector as just P naught, where this is understood to be the vector. If point P naught is x, y, z, then this would be the vector x, y, z. And it's a vector whose tail is at the origin and his tip is at the point x, y, z. So for any point P naught, we can think of there being a vector P naught. Then what I'd like to do is let's think of any other vector on who's in this collection that gives us a line. So let's think of this vector right here. And what we can do is we can think of this orange vector that I drew as the result of taking the vector p naught and adding some other vector to it. So what other vector would I have to add to p naught to get me to this orange vector right here? Well, by our triangle method of adding a vector addition, I'm going to add a vector, say this green one, right here. And notice that this green vector right here that I've just added follows the direction of the line. So let's do that again, but before our diagram gets too cluttered, let's put it over here. So I'm going to start off with some initial position vector, p naught. What is p naught? It's a position vector whose tip corresponds to some known point on the line. Then what am I going to do? I'm going to compute somehow something that I'm calling a direction vector, v. So v is going to be a direction vector here. Then I can think of getting to some other point on this graph by adding the first vector, p, plus the vector v. Let me just, since I'm color coding, let's do that. If I added vector p naught plus v, well, by my triangle rule for vector addition, I take the first vector, and then I put the tail of the second vector where the tip is, and that new tip is where I'm going to draw the resulting tip for my sum vector. So notice I'm able to get that orange vector. And in fact, I can get any other vector whose tip is on this line by adding some, this is the key idea, folks, by adding some scalar multiple of this green vector right here. For example, if we wanted to think about p naught, and here I'm color coding again, plus 2 times vector v, well, all I would do is I would take 2 vector v, which would be this vector right here, and then if I add p naught to this green vector, this direction vector that's been scaled by a factor of 2, so that's the vector 2v there, if I add them together, then I get another vector that's on the line. Maybe that's this one right here. And so by taking scalar multiples of my direction vector and adding them to my initial position vector, the sum of those gives me a new vector whose tip lies along the original line. Folks, that's a very complicated way to view a line, so please spend a little bit of time returning to this example here to make sure that that makes sense. And I guess just to drive the point home, let's also do p naught plus negative 1.5 vector v. And so what I would do is I would take the vector, and let me put the bar on that, I would take the vector p naught, and I would add to it the vector v scalar multiplied by 1.5, and then moving in the opposite direction. And so maybe that would be this vector right here. This would be this vector right here that I've just drawn. This would be negative 1.5 vector v. And when I add p naught to negative 1.5 vector v, that gives me this new vector right here. So again, this new vector, this blue arrow that I just drew, is the result of adding these two vectors together, and the tip of this new vector lies along my line. Okay, that diagram again got cluttered, so we're going to do it one more time, but this will be the last diagram we have to draw. So what I'm going to do is I'm going to take some initial position vector, p naught, and then I'm going to take a direction vector, which we'll call v. And then, folks, I'm going to think of my line as a collection of vectors. Maybe we'll call them p for position vector. We could use other letters, and we will. But my line is a collection of vectors that I get by adding this blue position vector, that blue initial position vector, plus what? Plus some scalar multiple of my green direction vector. How do I represent all of the different scalar multiples that I could possibly take on? By giving a parameterization there, such as t. And so as I allow t to vary for different values, I'll get different scalar multiples of this vector v added to my initial position vector, and each one of those will give me a new vector whose tip traces out, then in their entirety, traces out the equation of this line. So that's how we end up with an equation of a line, by adding an initial position vector plus some scalar multiple of a direction vector. And that's how we want to think of a line going forward. The last thing to say, though, is that we should always, whenever we do a parameterization, specify what values of t this could take on. And in our case, we want t to take on all values. We want all positive values, certainly, and all negative values and 0. So we're going to let t be from negative infinity to infinity. And always, folks, when you give a description of something, whether it's a parameterization description or as a vector equation like this one, you need to specify the domain, what the domain values take on. So what I'd like to do, folks, is show you something that I made here in CalcPlot 3D, where I've got an initial position vector shown in blue, and I've got a direction vector shown in green. And I want to show you again how that we can think of that as tracing out a line. What I'm going to do is I'm going to take and allow this green vector, direction vector v, to be scaled by some factor of t, and that will give me another vector as we move through here. So here you can see the result of adding what I'm doing to get, say, this vector right here, is I'm taking the blue initial position vector and adding it to some scalar multiple of the vector v. In this case, it would look like maybe that scalar multiple is about 3, right? Because this is about 3 times the length of this green vector. And so the points on the line can simply be thought of as taking that green vector v and scalar multiplying it by some number t and adding it to our initial position vector. All right, folks, I hope this helps. We're going to do some examples then in the next video.